Our objective here is to write a definite integral that will give us the area of a region between curves in the xy plane. So we're looking at number 2 here, and our region is bounded by the graph of y is equal to square root of x, the y-axis, and the horizontal line x is equal to 3. So here's our region, and we want to find the area of this region. And of course, there's no formula from geometry that would give us the exact area. So we have to go through a process similar to what we did for number 3, where we begin with approximating the area by using rectangles, because we know how to find the area of each rectangle. So we can approximate the area of this region by using rectangles. For example, I can find the area of each of these 3 rectangles and add them together, and that would give us an approximation for the area of our region. It would not be a very good approximation because we would have some extra area here. But how can you find the area of each rectangle? Well, you have to do the length of the rectangle multiplied by the height to give you the area, and then when you add together, you get an approximation. So here's what we have. F of c sub I giving us the length of each rectangle, and delta y sub I, which is giving us the height of each rectangle. So length times the height will give us the area of each rectangle, and we do it for 3 rectangles. As we've discussed before in our previous problem, we can make the approximation better by having more rectangles, each one of smaller and smaller heights. So for example, we could have 6 rectangles. If we have 6 rectangles, the height of each rectangle will now be a half unit, but it will be a better approximation because we will have less extra area. And we can take this idea and generalize with n rectangles, and you can make n 6 or 12 or 24, whatever is good enough for you in terms of how accurate you want your approximation to be. And when we take this idea to the extreme, we take the limit of this Riemann sum as the width of each subinterval, or in this case that would correspond to the height of each rectangle, approaches 0, so the number of rectangles will be approaching infinity, and the limit of this Riemann sum is a definite integral, and it would give us the exact area of our region. So let's write that definite integral for this problem. To write the definite integral correctly, you should begin by drawing a horizontal line segment, because that's how you're going to form your rectangle. And that's what we call an approximating element. So now you have to think in terms of how to find the area of that rectangle to get the correct definite integral for your problem. So how do you find the area of a rectangle? Well, you need to find the length of the rectangle, which in this case is given by the length of a horizontal line segment, and we know how to find that. We take the x-coordinate of the right endpoint and subtract from that the x-coordinate of the left endpoint. So we will have a function of y that will give us the length of each horizontal line segment, which will be the length of each rectangle, and it will be y squared minus 0. So now you need to multiply the length of each rectangle by the height, and the height is given by the length of this short little vertical line segment. That's delta y sub I, and that's coming from how you divide your interval from y is equal to 0 to y is equal to 3 into a number of subintervals to form your partition. But basically, delta y is going to give you the height of each rectangle, and that's why you're going to integrate not with respect to x, but with respect to y in this problem. Why? Because the height of each rectangle is a change in y between 2 partition points when you do your subinterval partition. So we know we should integrate with respect to y because the height of each rectangle is a change in y. So we have integration with respect to y. And height of a rectangle times its length will give us the area, and the length is given by the length of a horizontal line segment, which is given by this function f of y is equal to y squared minus 0, or just y squared. The last thing that you need is your limits of integration. what are your limits of integration? Well, your rectangles start here at y is equal to 0, okay, and they end here at y is equal to 3. And it's important that you understand that these are y coordinates. From y is equal to 0 to y is equal to 3 are the limits of integration, because your lowest rectangle starts at y is equal to 0, your highest rectangle ends at y is equal to 3, so that's what we have. So one thing to note is when you have integration with respect to y, your integrand is a function of y and your limits of integration are y values. So that's our definite integral that gives us the area of the region between the curves from number 2, and it is integration with respect to y.